Hello, and welcome to our Red Hat course on the fundamentals of Red Hat Enterprise Linux. My name's Chris Cayuet, and I'll be taking you through this journey where we explore the fundamentals of Linux itself and the environment available to you through Red Hat Enterprise Linux. We'll learn how to access tools through the command line interface, view, edit, and manage our files, create and manage users and groups and their access in the environment, as well as managing system processes and monitoring those processes so you have full control of your environment. We'll round it out by understanding how we can install and manage the software installed in our Red Hat systems so that we have a full understanding of the complexities that we have available to us with an ease of management afforded to us with Red Hat Enterprise Linux. Let's get our thinking caps on and let the learning begin. In order to perform the exercises in this course, it'll be necessary to have an installed version of Linux. If you'd like to take advantage of the Amazon free tier of available virtual machines, you can utilize the cloud provider, and we've included the instructions on how to do so. Here you can see that the course itself will run well in one of the free tier systems. These systems can be deployed using Red Hat Enterprise Linux version 8 and can run for 750 hours per month for 12 months at no cost. A key way to get the most out of this service is to make sure to shut down your instances when they're not in use. If you're not going to be returning for long periods of time, terminate the instance. The included instructions walk you through how to create an Amazon account and take advantage of the free tier systems. The step-by-step guide will show you how to deploy one of these free tier servers and utilize a Red Hat Enterprise Linux version 8 image in order to do so. Within the document, you can see the steps necessary. Generally, you'll start by creating an Amazon AWS free tier account. This will provide you with login credentials once you're complete to access the AWS console and create and manage your instances. When selecting your support plan, be sure to choose the basic plan, which is free. Once your account is configured and you're ready to utilize it, you'll go ahead and sign in to access the AWS console. From the Management Console, you can select the region nearest you. You do so in the top right corner. Once you've selected your region, you'll need to track down the AMI, or Amazon Machine Image, for the virtual machine you wish to deploy. Search for and select the Red Hat Enterprise Linux 8 HVM option. From there, you'll proceed through the wizard and you'll need to select the T2 micro size. This defines the virtual machine in the smallest size and conforms to the requirements to get the free tier access. Review your settings and launch your image. Next, you'll be prompted to select and create a key pair. This identification key pair is a security measure allowing you to securely access your system using an encrypted keychain. Directly from the system, you can generate and download the key pair you wish to use. Save this on your local machine, and you'll utilize this when accessing your system going forward. Further details are included, should you need them, on how to access your system itself using this implementation. Throughout the course, we'll explore much of the same material if you're a first-time user, so don't be intimidated at this point if you're still unsure of how you would access this Linux system. That's the point of this course. By managing the power and existence of the virtual machines in your environment, you'll get the most out of your Amazon free trial tier. Once you've stopped and need to resume an AWS instance, much in the same fashion of stopping the instance, there is a start button. When selected, your machine should go into a pending state and then a running state. Once the machine is in a running state, you should be able to proceed with connecting to the machine. A final warning that should you select terminate, this is a permanent destruction of the virtual machine. If you do accidentally terminate an instance, simply proceed back to the beginning of instance creation and generate a new virtual machine. Our references in the lab document include additional guidelines provided directly from Amazon should you need further assistance. Once deployed, you can utilize the Amazon instance to work through the exercises in this course. However you're able to get your hands on Linux, I look forward to having you join us through these exercises and explore the world of Linux and Linux system administration. Good luck, and let's get to learning. Linux, first and foremost, is a collection of operating systems. The generic term Linux describes any number of thousands of variations of Linux operating systems that all fit under the umbrella. While you may not have ever used Linux, you've certainly encountered it, probably on a daily basis, without knowing so. Much of the World Wide Web, banking systems, applications you're used to using, as well as point-of-sale systems at the places you shop or eat, are all powered by Linux. Even in your own home, smart televisions and smart systems that are integrated into your daily life can have their foundation or even back-end systems such as cloud services that run within Linux infrastructures. But why would you want to learn about Linux? I think there's many good reasons, but we find a few specific categories of individuals who need to explore Linux in a more robust sense. If you're someone familiar with Windows workloads and are now needing to diversify your knowledge because the environments you administrate include Linux operating system-based servers and systems, well, now you'll need to begin exploring this new world of operating systems. Additionally, if you're doing application development, you need to consider the environments that your workloads can run on. It's quite common to host applications and back-end server systems on Linux environments, and it'll be useful for you to be able to explore your options when it comes time to stand up that infrastructure. When you work in the cloud, much of the cloud runs atop systems that are all running Linux to make the harmonious and available elastic clouds we've come to appreciate serve our daily needs. And when you come to the more modern mobile applications and Internet of Things implementations we see in our daily lives, Linux is almost certain to be under the hood. But what makes Linux great? Linux is great for a few reasons, and if you talk with anyone who's converted or administrates hybrid environments that include Linux, they'll be able to typically line out what is different for them in Linux systems and why they even prefer them. The first thing that makes Linux great is that Linux is open source. When we use the term open source, we mean that the entire code base that builds the operating system is available to one and all to explore, enhance, and alter to their liking. This means that there's an entire community of system administrators, developers, and users who co-contribute to build the great Linux distributions we have at our fingertips. This contrasts from the proprietary or closed source environments we know from companies like Microsoft who give us Windows. Microsoft Windows is an operating system that only Microsoft has access to the code base that builds and operates Windows. You're reliant on a specific entity to deliver new features as well as bug fixes on a timely fashion. There was a day and age where that was a primary choice, if not an only choice. But in the world of open source technologies, especially as it pertains to the operating systems of Linux, you now have thousands upon thousands of users who share their knowledge and help enhance the Linux environments that we use today. Linux also includes an easy-to-use command line interface. This means that at your fingertips, you have the ability to script and alter the environment and its behaviors with very simple, easy to learn and understand commands that you'll grow in your repertoire as you learn more and more Linux. Also, Linux is a modular operating system, meaning that you can replace or remove components that are not to your liking. If you need to add software, there's entire libraries of software packages that you can install. Would you like to alter its behavior on how it performs or operates? You can dive into the code base for each individual application and alter all of the above. With open source, the entire behavior of the environment is at your fingertips and backed up by an entire community of contributors to the code base that help to enhance the Linux and Linux environments. Linux isn't the only thing in the world that's open source. There's entire catalogs of open source software in the world. Software that allows the community to view and alter and enhance the code base adopts the philosophy of open source software. When we all work together to create great applications and operating systems and environments, we're guaranteed to have something more robust and more reliable over time than a proprietary option that may exist. When open source software is created, it is licensed under a collection of open source licenses. There's many that may exist in the world, but the general philosophy under open source licenses is that you can use at your discretion, and if you contribute, you must contribute freely to allow others to use at their discretion as well. There's an onus to always give credit to those who've contributed, but to allow others to freely use the software we build together. And that adds an exclamation point. I did use the word free to use. And in most cases, open source software is absolutely given and shared at no cost to an end user. This is very powerful in an enterprise environment when you consider so many budgets and bottom lines rotate around software or technology expenditures. Knowing that you can rely on libraries upon libraries of open source software to fuel your business means that you can spend less on technology and software implementations and more on your bottom line to deliver your product, software, and experiences to your customer. 4 main benefits come out of adopting open source philosophies and technologies. First is you'll have the control of your code base and the software you run within your environments, fully adaptable to meet your needs. Second, with a community behind you, you can access training from all the best and brightest minds who've built, used, and continue to enhance the software you've adopted. Third is the security implications of having one and all help ensure that you have enhanced, robust security across all surfaces of your software stack. And lastly, stability. Stability is always a key factor to the community to ensure that when software is delivered, it runs stably, and runs reliably. This is what allows you to trust an open source piece of software powered by its open source community to run within your home, business, or enterprise applications. Open source software always adopts an open source license under which it is distributed. Many different licenses exist in the world today, but they have some general philosophies that seem to be the same across all. In general, copyleft licenses encourage the reusability and design structure that keeps code open source, meaning free to all to use and share. Permissive licenses are also designed to maximize code reusability. An example of a copyleft license is the GNU General Public License, or GPL. This is a commonly used license for distributing open source software to one and all in a share and share alike type mindset. Permissive licenses include phrases that say you can distribute and utilize software as long as you preserve the copyright and integrity of those licenses within the software. An example of permissive licenses are the BSD or Apache software licenses, backed by those organizations. We've mentioned that open source software is powered by the communities behind them. But who actually develops this software? When we say community, communities are comprised of individual users as well as enterprises who have adopted that software alike. This leads to a large number of users who end up contributing to the code base itself to ensure the stability and reusability of the products that they're enhancing. In this chart, you can see a list of companies that have made corporate contributions to Linux. These companies are across all sectors and see it in their interest to enhance the code base that they run within their walls. When companies like Red Hat enhance products like Red Hat Enterprise Linux, they share that enterprise-level code with one and all who adopt the product. You can see a large number of companies in this graph alone who found it in their best interest to enhance different open-source software and share those enhancements with the world at large. All of these companies simultaneously benefit from the community of users outside their walls who are doing the same, enhancing and fixing bugs within the products they've adopted to run in their enterprise situations. We saw Red Hat on the graph, but who is Red Hat themselves? At Red Hat, we're a leading provider of the world's largest distribution in the enterprise sector called Red Hat Enterprise Linux. This software is used to power some of the world's largest clouds, infrastructure, web-based servers, middleware, storage solutions, and virtualization technologies. It runs on every continent and inside every sector of the market. The role Red Hat plays within the ecosystem is to ensure an enterprise license is available for the software we provide and the community supports. With Red Hat-backed licensing atop a Linux distribution, you know you can rely on a corporate entity to help provide the enterprise-level support, releases, and features that are needed by the world at large. Red Hat layers a service layer atop the open source software to enable enterprise solutions that can be trusted in any walls. While Red Hat Enterprise Linux is our flagship product from the inception, we contribute in many other open source technologies, such as OpenStack, a cloud orchestration tool, or OpenShift, a container management platform. So what is a Linux distribution? Red Hat Enterprise Linux is one of a catalog of distributions that exist in the world. A Linux distribution itself is an installable operating system that is supported by a community of users and gives a specific delivered experience, package set, and toolkit to the end users who install that operating system. As there's many preferences in what this would look like, so there are many distributions of Linux that exist in the world, each of which offers the opportunity to begin from the foundation of the operating system and customize and contribute going forward. The beginning of Linux distributions all started with the kernel. The kernel serves as the main brain of the operating system that any version of Linux would run. Linus Torvalds is the creator of the very first Linux kernel, adapted from the existing Unix-like kernels of its day. Since the early 90s, the Linux kernel itself has run and been adapted forward in time. This includes contributions from all walks of life and all continents of the earth. The Linux kernel itself is licensed under the GPL, or GNU Public License. So at the core of every Linux distribution is the kernel to get started. From there, you need to continue to layer on other technologies, software from open source communities that build out the rest of the features for your operating system. Building out a Linux distribution can include any number of pieces of open source software to flesh out an entire operating system. Things that provide Windows-based graphical environments, web servers, user management toolkits, or any number of solutions that you may need in your specific distribution. Once a set of software is collected, it can then be stamped as its own distribution, forming its own community and set of users who contribute to and maintain that specific Linux distribution. Distributions can vary greatly. They can be tiny and only look to serve a single purpose. These are commonly found in things like remote control or a smart television that provides some simple features for a very specific purpose. A distribution could alternatively be very large, such as those that power some of the world's largest supercomputers. In the end, Linux distributions exist to solve almost any problem we have in the world today. Exploring through the catalog of Linux distributions is certain to reveal one that meets the needs in your business. At Red Hat, we participate in the community that builds out the various pieces of open source technology that go into the great community of software. This helps us understand the lay of the land for the evolving technologies we see running in the world today. It helps us also contribute and shape the future world of tomorrow. As software matures, we then take those contributions and integrate them into our community-driven Linux distribution we call Fedora. Fedora is a free working environment that allows you to taste test the Red Hat Enterprise Linux environments that will end up being released into the commercial environments. It's a first look at what will come from Red Hat Enterprise Linux and an area where we can explore and try new technologies to see if it meets customer needs. Once software has been identified to be included in Red Hat Enterprise Linux, it goes through a stabilizing or hardening process where we ensure that it runs and runs well in commercial applications. From there, we license it and release a new version of Red Hat Enterprise Linux that our end customers can trust to run within their commercial environments for years to come. Here you can see a flow of that work. First, we participate in an array of community projects. Those that prove worth their salt to be included in the operating system are then integrated into our environments and tested in environments like Fedora. Finally, those that are required for integration into our commercial applications are stabilized and included in the future releases of Red Hat Enterprise Linux. Here, we commercially license and support those for enterprise needs. If you're interested in trying out Red Hat Enterprise Linux, download an evaluation copy to see if it meets your needs. Once you're licensed with Red Hat Enterprise Linux, you can rely on Red Hat to deliver a stable and reliable enterprise operating system for whatever commercial applications you need. This concludes our introduction to Linux itself. In the next section, we'll explore the command line interface. In this chapter, we'll be looking at accessing the command line. In Linux, it's imperative that you learn how to utilize the command line interface to most powerfully adapt and control the Linux environment. When logging into a system, one of the first tools you'll want to learn as a system administrator is how to access the command line. Here you can see a system running Red Hat Linux. I'll log in using the student user. Supplying the password and the graphical user interface takes us directly to the desktop. In order to launch the command line interface, we'll utilize a program called Terminal. From our Activities menu, we can find the terminal listed in the sidebar. By clicking Terminal, the window should open. Now that we have access to our terminal, let's understand what the shell itself is. A command line interface is a text-based interaction between you and the operating system. It allows you full control of the environment, as long as you know how to wield it properly. When you launched Terminal, what opened is what is known as a shell in Linux. In particular in Red Hat, the default shell is known as Bash, or the born-again shell. Once the terminal is opened, your shell presents you with a prompt. The shell prompt shown here is one for a regular user. It will end with the $sign to denote where the prompt ends and your commands can begin being entered. When you're running as a super user in Linux shells, the end $sign will be replaced with a pound or hash sign. This denotes that ascended privileges are in usage. The root user is known as our administrative or super user within the Linux environments. By denoting on the prompt this change from a $sign to a hash, you know that you have the proper ascended credentials whenever trying to access more secure or restricted areas of the operating system itself. Here you can see a prompt that is showing the change from the $sign to the pound sign and noting that we are using the super user. The username in this case shows as root. The Bash shell is a powerful way to control your environment and expresses an entire scripting language that you now have access to for controlling and automating tasks. Shell scripting is an evolving skill as you grow in your system administrative journey and will become something highly useful as you wish to do more and more complex tasks within your Linux environment. Now that we've taken a look at the Bash shell, let's see the first few commands that we can experiment with to start growing our skills. In this section, we'll take a look at shell basics. When working within any shell, such as the Bash shell that we've just explored, commands that you enter have several basic parts. First, there's a command that you'll wish to run. There are many commands in Linux environments, and learning them will only take time. Every command can have many options that you can express to adjust the behavior of the command itself. And lastly, for each command, you'll need to supply the arguments for that specific command. Depending on the command that is being used, the type of arguments you'll supply will vary greatly. Once you know the name of a command you wish to run, you can supply additional options to alter its behavior. We express these options with using a dash or a dash dash syntax. Depending on whether you're using one or two dashes will depend on whether your option is a short form, such as the dash A, or a long form, such as the dash dash all option that we see here. Many options may be necessary to alter the behavior of a command to your liking. Once you've iterated through all the options necessary for your command, you'll then supply additional arguments. Oftentimes, these arguments are coupled with the particular option. Later on in the course, we'll take a look at how to explore command options by using their manual pages. But let's have a quick look at a simple command user mod within our own shell currently. If I were to simply enter the command user mod, it takes arguments and would, upon pressing enter, express all of the various options you may have available to you for that command. We can see that the -L argument will lock a user account. If we had a particular user account we wish to lock on this system and disable from usage, we could supply the command usermod, the L argument, and then supply the user whose account you wish to lock. That's an example of putting together a command, an option, and the arguments for that command. Now that you've seen a command put together with its options and argument, that covers the shell basics. In our next section, we'll take a look at logging into your systems. Logging into a local computer. From a graphical user interface, we would be presented with the users on the system that we can log in with. Any user whose credentials you have, you can access when you have direct access to the machine itself. Here, I'll log in as the demo user. Supplying the password for this user should allow access to the graphical user interface. Once the graphical interface loads, and we have access to all the applications within the operating system, we can browse into Activities and launch the piece of software called Terminal. In a Red Hat environment, this will launch us into a Bash shell. From here, we can begin supplying commands, their options, and arguments to control our environment. When you're logged in this fashion, you're utilizing the Linux machine's physical console. Once logged in, the physical console supports many virtual consoles, each running a separate terminal. Every virtual console supports an independent login session. If you were to be logged in with multiple users or switch users during your login, you would create and switch to a separate virtual console. You can switch between these consoles using the Control and Alt keys plus one of the function keys F1 through F6. Most of these virtual consoles run a terminal providing only a text login prompt, and if you enter proper credentials in the form of a username and password, you'll be able to access a shell prompt. Computers that have graphical login prompts will only be available in the latter virtual consoles, namely virtual consoles 4, 5, and 6 in typical environments. You'll access those virtual consoles by using a combination of the Control and Alt keys and the corresponding function key, F4, F5, and F6. As we just saw from within our graphical environment, we can utilize the terminal command to then access a shell prompt. Many systems, however, run without a keyboard or monitor attached and may not even install a graphical user environment. Systems configured in this way are known as headless servers. A headless server would not have available to you the physical console to log into and would require remote access. We'll take a look in the next section of how to access headless servers via remote or network-based logins. We learned that many Linux systems can be configured as headless servers, or that they don't have direct physical access to the machines or keyboards and monitors connected to those systems. In these configurations, we need to understand how to access those machines over the network. Within Linux, the most common way to get a remote shell access to one of these systems is by using the application SSH, or the Secure Shell. The Secure Shell application encrypts your connection from wherever you're located to the remote system to allow you to pass traffic safely and securely and access those remote systems over the network. Here you can see an example of a sample SSH command. Dissecting this command a bit further, it requires a few pieces to form an argument. First, we'll invoke the SSH command itself. In order to describe to SSH where we would like to connect, we'll need to supply two main components. The first is the remote user you wish to use when accessing a remote host. The remote host represents the machine you're logging into, and the remote user represents the set of credentials you're going to use when accessing that machine. Once you've supplied this argument and press enter, the password for the remote user will then be requested. An important thing to understand is that when you type this password, your characters will neither show on the screen nor will the cursor move. This can be confusing for first-time users, as they seem to think that their keyboard is simply not inputting the characters. It is for your security that the number of characters that you're entering is not displayed on the screen, nor is the cursor going to move. Simply type the proper credential password and press enter. Let's have a look at an example of this from a terminal itself. I have in my environment a server A, so I'll try to connect to server A using my demo user. If properly configured, this should lead to a prompt that prompts me for my demo user's account and provide access to that system if the user exists. The command we'll use is SSH, and then we'll declare our user of demo at the server we wish to connect to, and I have a system called server A. If I press enter, it will prompt me for my demo user's name. After being prompted for the password and supplying the correct information, I can see that I now access server A. If it's your first time for this user to connect to the system, you should be presented with a yes or no prompt that explains that you'll be accessing the system for the first time. If you wish to proceed, type yes and hit enter. This will handshake and add a fingerprint so that the system is aware that it is familiar with your user and has now been accessed for the first time. Depending on how systems are configured, additional messages may be displayed. Your results may vary depending on the type of environment you have configured. In this section, we'll learn how to log out of connections we've established. It's important to know how to break the connections you've established using SSH. It's very easy to do so, and you have two main options. One way to do so is to simply type the command exit, which instructs the terminal to sever the connection. An alternative to the exit command is the shortcut Ctrl+D. Let's take a look back in our terminal and see how we sever that connection. Here you can see we're still logged in as the demo user on our server A system. By typing exit, The connection to server A is closed, and we're returned to our workstation system. That concludes our section on logging out. I'll see you in the next video where we look into some hands-on exercises using these new skills. Now that we've looked at how to open up and utilize a terminal in the most basic sense, we should dive in deeper into using the born-again shell, commonly known as the bash shell. The general behavior of executing commands in a bash shell is to type out a command, any of its options you wish to use, and the arguments the command requires. Not all commands require arguments and options to perform work, but you'll learn how to use each command in its own proper way throughout time. Once you've completed forming your command, you'll simply press enter to execute the instruction set. Once the work is complete from that command, it'll return you to a prompt. Here, you can see a simple example command. In this example, the whoami command returns the name user, or the username that the current person is logged in with. Oftentimes, you may need to either string together commands, or they may need to take up more than one line. When you need to do this, simply use the semicolon as a command separator. Commands that take up more than one line can continue to be typed, and the command should wrap to the extra line. The semicolon is one of a number of meta characters that we have throughout Bash. We'll see more of these throughout the course, but tuck that away for now. In the example shown here, we're using the semicolon to string two example commands together. We would simply type command 1, the semicolon, and then command 2. These are placeholder commands, but represent any command, its options, or arguments that you'd like to string together in this fashion. That's a basic overview of command syntax. In our next segment, we'll look at some example commands. An entire library of commands are now at your fingertips now that you have access to the command line interface in a Linux environment. As you grow in your Linux skills, so too will the list of commands you're familiar with using. Throughout the rest of this course, we'll explore many of these commands as well as how to look up the manual pages for each and explore the further usage of their options and arguments in more robust situations. To begin, however, we'll need to equip you with a few simple commands that are commonly used throughout all Linux environments. Here, you can see an example of the date command. Another helpful command that you'll need is the password command, or passwd. This allows a user to change their own password. In many system administration environments, there can be timers that are equipped to trigger this interaction so that you can rotate your passwords and keep the security of the environment. In this example, however, we're just looking at how to invoke a simple password change for the current user you're logged in with. Let's invoke the passwd command for my current demo user. The first thing it'll ask for is the current password. Now that you've entered the current password correctly, you can supply a new password. You'll be asked to re-enter this after the initial entry. Note that while I just put in a simple password, it warned me that that's too short for an appropriate level password. Let's try again and use something a bit stronger. Alright, I'll once again enter my current password, and now the new password. Here, the password fails a dictionary check. This means that the word I entered is too commonly found in the dictionary and thus would make for a bad password. Now let's go ahead and set a proper strength password. We'll supply our current password, and now the new one. Now that I've supplied an appropriate length and strength of password, my password has now been updated. When I go to log in with this user going forward, I'll need to supply this new password. Now that we understand how to rotate our password, let's continue looking at some additional commands. By design, Linux does not require or enforce specific file extensions. In lieu of that, we have the command file. The file command scans a file and determines what kind of content is within that file. Let's take a look at an example on the command line. Here, I'll look at the credential password file. We can see it's known as an ASCII text document. Other examples exist as well. In this case, let's look at the binary version of the same file. Here we can see a much different kind of file. The file command is able to identify the two different types. This will be helpful as you explore the operating system and need to understand the types of files you're encountering. That concludes a look at just a few of the simple commands we'll encounter in Linux. See you in the next section where we start working with how to view and edit files. In this section, we'll take a look at viewing the contents of files. Linux itself is just an elaborate collection of files that work together to form an entire operating system. With this being the case, viewing files will become very necessary as you explore the operating system environment. Many commands interact with files directly and will need to equip you with several so that you can appropriately navigate and alter the Linux environment. First command to know when you're looking at files is the cat command, C-A-T, short for concatenate. What this does by default is output the contents of a file to your screen. As we recently interacted with the /etc or etc directory file passwd, we can try that now. We'll simply use the command cat and then the file we wish catted. The file is then concatenated or printed to your screen. If we had multiple files, we could simply string them along in the command and it would output the contents of both. Here you can see an example of two files being concatenated to the screen. In file 1 is the words hello world, and file 2 would contain the Introduction to Linux command entry. By calling these together, the contents of both files are output to the screen. Oftentimes, however, as you concatenate these files to the screen, they have very long output and don't fit on a single screen. The less command allows you to display the contents of a file one page at a time on the screen. Let's take a look at the difference between catting the etc password file and using this new less command. When we cat etc password, we can see that there is a very large file that gets printed. If you were to scroll up, you'd be able to see this. If we needed to look at this one page at a time, the less command provides us that availability. Let's try to less etc password. Here you can see just the top of the file. You can navigate up and down the file using the arrows, up and down, or the spacebar to go a page at a time. When you're done perusing the file, the Q key will exit out. Sometimes we need only see either the beginning or the end of a file. While less lets us load up the entire file and navigate through it to browse, the commands head and tail will give us just the first 10 lines in the case of head, or the last 10 lines in the case of tail from the file. This can be helpful if you're looking to see if you've just added an entry to etc password, as those entries will go in at the bottom of the file. Additionally, when looking at a document, you may just want to peruse the very first entries to see what the purpose or contents of that file may be. Let's try both of these commands on the etc password file. The head of etc password should contain the first 10 entries we have within the password file. Additionally, the tail command would have the last 10. If we wanted a different number than 10, we can also pass a flag or option that allows us to specify the number of lines we wish from either the head or tail command. Both of these take a -n option. If we wanted to see the first 3 or last 3 lines, we could use either of these commands to do so with the argument -n3. Here, the head command with a -n3 of etc password would give us the first 3 lines. As I mentioned, the tail would do a similar thing for the last 3. Another helpful command that you'll want to utilize from time to time is the WC command, short for word count. The WC command can be used to count words, lines, or even characters of a given file. Let's try some of these options on the same file, etc password. By itself, WC will give us the output with 3 numbers. These 3 numbers correspond to the lines of the file, the words of the file, and the number of characters in the file. If we only wanted one of these pieces of information, we can specify with the flags -L for lines, or we could specify -W for the number of words, or we could specify -C for the character count of etc password. As we saw in each of those, we would have the matching value that came from the full output of etc password. That concludes our section on viewing the contents of files. I'll see you in the next section where we learn a very specific and powerful technique in Linux known as tab completion. Provides a very helpful shortcut when typing out commands in Linux. The more keystrokes you can save when working from a command line interface, the faster you can be at system administration tasks. Enter the tab completion concept. By using the tab key, you can attempt to automatically allow the operating system to complete words or commands that you're typing out. This is helpful throughout the entire operating system when forming many commands or interacting with files in any given circumstance. You can see an illustration here which tries to describe the behavior of tab completion. Tab completion is more of a time saver than anything, and it is always acceptable to type out these commands. However, you get several main values from learning how to use tab completion. The first value is that tab completion will automatically properly spell commands or entries you're trying to complete. This eliminates an opportunity for you to make typos and errors in the commands you're typing, especially challenging when you're using or working with long file paths or file names. The second thing tab completion can show you is the options that it has available to it given the first few characters you've typed. In this example, we see that typing PAS and tapping tab key twice will list out all the commands available to you that begin with the first three letters PAS. If we then supply another letter S, we've eliminated the additional options, and by pressing the tab key once, will be auto-completed to the passwd command. We can then proceed with a password change interaction. To sum that up, if you were to press the tab key once and an automatic completion cannot be found, pressing the tab key a second time will list out the possible options the operating system has available. When you have a unique match when pressing the tab key, the operating system will automatically complete that word. Let me show that from the command line as well. Using that same example, I can type PAS and press tab. By pressing it once, nothing has occurred, but pressing it again shows me those three options. By simply supplying one more letter, in this case, I'll say T, and pressing tab one time, I complete the only match that starts with PAST, in this case, the paste command. The same concept is also helpful when working with file names. We've continually worked with the etc password file, so let's take a look at what our options are when we try that. I'll use the cat command to simply provide a command that then takes an argument of a file name. If I type /etc and supply no other letters, the directory contains many files. In this case, more than you may want to display on the screen. If you did want to display them, you're given the option to present those by typing Y for yes or N for no. If I say yes, they're listed out. In this case, more than fit on the screen, and by pressing spacebar, I can continue to see those options. I'll continue to press spacebar until I've run out of all my options. Now I'm returned back to my prompt where I was typing out my command. I know that my etc password file starts with P, so I'll type a P and press tab. It doesn't auto-complete, so pressing tab again will list out all of the matches that begin with P. We can see the list is narrowing. If I type AS and hit tab, it automatically completes the etc password. In our next section, we'll take a look at how to continue long commands on another line. As you grow your repertoire of commands, you'll learn that many commands take a long list of options and arguments to properly form their work. When you consider that you can string multiple of these commands together, you can see how the entries could end up running longer than a single line. To cleanly enter commands across multiple lines, there's some easy techniques in Linux to allow you to do exactly that. We utilize the / character in order to tell the terminal that we are continuing our command on the next line. This continuation command allows us to take as many lines as necessary to cleanly enter our command in a legible form for us to read, while also continuing to take up as many lines as necessary to complete the work. You can see an example of this in the box below. Here we're using our continuation command, the / at the end of each of these lines. This tells the terminal that these lines should be listed as a single long-running command. In this case, we're using the head command and asking for the top 3 lines of 2 different files. Let's give this a try. Head-n3 for the first 3 lines of, let's use the / so we can continue the command on the next line, and we'll list our first file. We can hit the / command and the enter key, and we do not yet execute the work. Here, I'll go ahead and say etc password. Okay, and so that I can continue listing out additional files, I'll put a /, hit enter to go to the next line, and I'll list out the first 3 lines of another file, in this case, etc group. Just to recall tab completion, if I type GR and hit tab, there's many options. I can then further type GROU and it will autocomplete to Etsy group. Don't be confused by the tab completion output. It is not considered part of the command, although you're seeing it on your screen. Now that I'm ready to complete the command and execute it and receive that output, I can hit enter. We see that we get the first 3 lines of both of those files. That concludes our section on how to continue commands on another line. In our shell, the list of commands we've run sequentially is stored so that we can review the history of commands we've executed. The command available to us to review this is the history command. Let's take a look at that output now. To see the entire list of our command history, we use the history command. We can see all the various work we've done throughout the course. If you wish to re-execute any of your previously run commands from the command history, note that they are enumerated in the list. If I wanted to rerun any of them, I can use the exclamation point, affectionately called the bang in Linux, and then the number of the command that we wish to rerun. If I wanted to run a previous command that matches by string, I could use the exclamation point and type that string, and it would run the most recent version of that command. Let's give a few of these a try. If I were to want to run the word count command on Etsy password, I would simply need to type the exclamation point and the number for the command, in this case, 19. Let's give that a try. Bang 19 should rerun the WC Etsy password command. Additionally, if I wanted to run the most recent version of the tail command, we can see that on line 18. I should be able to just say bang tail, which does in fact run tail-n3 Etsy password. When perusing the history of your commands, you can navigate through that using the up arrow and down arrow as you see fit. The left arrow and right arrow will navigate across the line. If you needed to edit a command before executing it, you can do so in this fashion by using the left and right arrow keys to navigate to the point in the line where you needed to edit, and then making your change and running the command. A few other shortcuts exist as well that are helpful in this case when perusing command history or trying to reuse it in your current work. Escape and the dot or Alt and the dot give you these additional shortcuts. Here's an example of using the escape and dot to rerun the last command. The escape command will recall the last argument used in your previous command. The last argument used in our previous command was the name of the file Etsy password. So if I needed to cat that file, I could cat and then use the escape and period key. Don't hold the escape key or it'll start going crazy on the terminal, but you can see escape and period will supply the last argument, namely Etsy password, into my current terminal line. I could then cat the file. In this section, we'll take a look at editing the command line. When beginning to work with the command line interface, learning all the tips and tricks available to you can seem daunting. However, each one enhances your ability to work quickly and efficiently. This is really the key to becoming a great system administrator and feeling comfortable in a Linux environment. When working with commands on the command line, jumping around to and from the different parts of commands and navigating the command line with ease offers you many shortcuts in improving your performance. Here's a great list of commands that help you navigate the command line and edit around using some hotkeys available from the keyboard. In this table, we have a list of some of the most commonly used hotkeys for navigating around command line editing. Control-A, for example, will jump back to the beginning of the line. Control-E jumps to the end of the line. Control-U clears from the cursor to the beginning of the command line. So if you have the cursor placed in the center of a command, you can erase things previous to that. Control-K does the opposite and will erase from the cursor to the end of the command line. Control left and right arrows jump from word to word as you navigate through. So jumping from word to word going to the left will take you closer to the beginning of the command line, and by using the right key would jump you word by word towards the end of the command. Control R is probably the most popular hotkey to use in this case. It is a reverse command search and allows you to type the Control R and start typing out a command you wish to use. This then searches back through your command history, bringing up the last used commands that match what is typed. Let's take a look at a few of these. If I were to want to type a really long command, I could then navigate around. Control A would take me back to the beginning of this line, and Control E would jump to the end. If I wanted to get rid of some of these words, I could easily use the Control U to get rid of the words at the beginning before the cursor, or Control K to delete everything after the cursor. If I wanted to move left by word, I can hold the Control key and left to jump a word at a time, and the opposite with the right key. Control R command does what's called a reverse history search for the commands, a reverse command search. Here, a new prompt is entered, and then you can start typing the command you wish to complete. I recall that we were using the tail command previously, and if I start typing TA, I immediately match on the last word. If this was what I needed to run, I could then press enter, and it would execute that command. Using these shortcuts helps you craft commands quickly and efficiently, as well as search back through and reutilize commands you've been running previously in your history. This concludes our section on editing the command line. I'll see you in the next video. Welcome back to our guided exercise on accessing the command line. I've already connected to my instance using SSH, so go ahead and do so now with your own unique information, and then we'll jump to step number 2. Here in step number 2, we're asked to use the date command to display the current time and date. From the command line, simply use the command date. In the example shown in the instructions, there's a slightly different user prompt that should match something similar to what you're seeing, of course with a different IP address. In my case, I'm using a localhost instance, so my prompt looks slightly differently. However, it remains the same, that ec2-user is our username, and then the information after the @ symbol specifies the host that we're connected to. The last bit of information, shown here as a tilde, describes the local directory that we're working from. We'll take a look at that information later in the course and understand how to interpret it, but it's interesting to note that it's described directly in our prompt. After typing the command date, you press enter, and then the output of the date command is displayed. This information certainly changes as your date likely conflicts with my own. We can further augment this, shown in step 3, by some additional arguments to the date command. In this case, we're asked to use the plus, %, and R argument with the date command in order to augment the output. Let's do so now. Here you can see we've adapted the output to where we simply see the time portion of the date output. Task 4 asks us to determine what kind of file is the file user bin zcat. We'll use the command file in order to do so. The command file takes the argument for user bin zcat and returns that user bin zcat is a shell script and ASCII text executable. We'll use the WC or word count command to display the number of lines, words, and bytes in the script user bin zcat. Instead of retyping the file name, you can use the bash history shortcut of escape and the period key pressed at the same time. This will reuse the argument from the prior command. So here we'll type WC, and then we'll hit escape and period at the same time, and it'll automatically supply the argument used in the previous command file. We can then hit enter to see the output of the WC command to see that it's 51 lines long, 299 words long, and 1,988 characters long. Task 6 asks us to use the head command to display the first 10 lines of the file that we've been working with. Try to recall the escape plus period key shortcut here. The more shortcuts you have at your fingertips, the better of a system administrator you are, simply because you can execute your work more efficiently. Let's go ahead and do the head command now. Head, and then I'm pressing escape period. Oh, typo on my part. Double tap there. Escape period, and it auto completes that argument once again. We can then hit enter to see those first 10 lines. Now we want to display the last 10 lines using the tail command. Again, I'll use that same escape and period shortcut. Nice, so quick to type that out as opposed to using tab completion, which would also be quite quick, or worst case, actually typing out all of these characters. That concludes this guided exercise where we used our first commands in the command line interface. I hope you're starting to get excited as well as a little bit familiar with moving around in Linux. I look forward to seeing you in our next video. See you there. In this chapter, we'll look at managing files on the command line interface. Throughout this chapter, we'll learn how to copy, move, and understand the appropriate places for the different types of files that comprise our operating system. This will enable you to fully manage your environment, as Linux is just a complex organization of files to create an entire operating system environment. By the end of this chapter, you should feel comfortable copying, moving, creating, deleting, editing, and organizing the files, utilizing the bash shell from a terminal within our Linux operating system. You'll learn how to organize the files in Linux for their particular purposes and functions, as well as the many directories that are vital to understand their purpose throughout the hierarchy of files. In this section, we'll look at the Linux file system hierarchy and understand the purpose and function of the various directories that comprise the Linux operating system. Linux operating systems are just a collection of elaborately organized and purposed files. As you start to explore Linux, it's critical to start learning the particular purposes of the various files and folders located throughout the operating system. This collection and structure of folders and files is known as the Linux file system hierarchy. In the diagram shown here, we see an inverted tree structure of the various files and folders that are critical within the Linux file system hierarchy. When referring to the pathing of these particular files, we always start with a /. The / itself is its own directory we call the root directory. All folders are created within some pathing below the root directory. When we wish to reference certain folders, we'll use a pathing that starts with the / to do so. If we wish to reference this particular folder here, we would need to reference not only the /, but also the parent folder that it comes from. It would result in a path that starts with /usr, another /, and then the folder bin. If we were to look at a folder like the issue folder specified here, we would expect that it would be within the /root folder, the etc folder, and would exist somewhere off of this chain. We would ultimately refer to the folders with names like folders and subfolders, or directories and subdirectories. We could, for example, refer to this as the root directory with an etc subdirectory, oftentimes referred to as etc. It's in this way you'll be able to describe the proper location in the Linux file system hierarchy of the folders or files you're interacting with. We'll use this nomenclature throughout the remainder of the course. Next, we should understand the proper purposes of some of the directories and subdirectories located in the operating system. Expanding further on the diagram, let's look at each of these subfolders to understand the intended purpose for the files and subdirectories contained within. The /usr, or user directory, includes installed software, shared libraries, and the files that are typically used for read-only program data. When we talk about the /usr bin directory, that contains the files that specify user commands. User sbin has system administration commands. The /usr/local directory is intended for locally customized software for your specific user or implementation. Next is the /etc or etc directory. This directory is intended for system configuration files. Next is our /var directory. Variable-specific data is contained within these files. Files that may change in their content dynamically, such as database configurations or web content, are typically located within the var directory. /run contains runtime data files. Typically, this would include process files that control the locking mechanisms for system resources for the applications that are currently running on the system. In prior versions of Red Hat Enterprise Linux and other Linux operating systems, this would contain data similar to what we would have found in the var run or var lock locations. Next is the /home directory. Home directories are where regular users store their personal data and files. This could also include configuration files that customize the behavior of software applications unique to that user. /root, while confusing, is not to be confused with the / directory we call root. The / directory is the root of the file hierarchy, whereas /root is the home directory for the superuser administrative account root. This can become confusing, as now we've reused the term root in several locations. There's first off the root user, which is our super user administrative account. We then introduce the slash directory as the root directory of the file hierarchy. And now we have a third instance of slash root, which is the home folder for the administrative user. With time, you'll be able to keep all three of these clear. Next is the slash temp folder. As you may guess, this is where temporary files are written. This is a world writable space, meaning that all users have access to this location. However, some protections are in place to allow any user to only manage or delete the files they've created. Oftentimes, the slash temp directory will have automatic cleanup procedures to delete files that have not been interacted with for 10 days. This is an intended safety measure of the slash temp directory to keep the workspace usable and uncluttered by all users. However, it is key to understand that behavior so that you don't lose your work if you've kept it in this location. The slash boot directory are files required by the operating system in order to complete the boot up process. And lastly is the slash dev location. This contains special kinds of files we call device files. These device files directly correspond to the hardware that our system will access, such as hard drives or other devices installed physically within the machine. This can also include a set of virtual instances or devices that we've presented to the environment. Examples of that could be virtualized storage devices. In our next section, we'll learn to locate files by their name. I look forward to seeing you in the next video. Welcome back to our course. In this section, we'll learn about locating files by name. Once we're done, you should be able to specify the location of a file or directory by its relative path to the current working directory or absolute location within the file system. You should also be able to determine and change the working directory, as well as list the contents contained within that directory. As we started to explore in the previous section, we need to learn the pathing, or how to specify where a file or directory is located within our operating system. There's two main ways we'll do this. Absolute paths and relative paths give us two different ways to declare the location of a file or subdirectory within the operating system. Depending on our use, we may need to describe them in certain ways, either relative to other locations of files and folders, or absolutely from the root of the file system itself. Understanding both of these is critical, as you'll need each in their own places when you do system administration work. If we consider the first context of absolute paths always describe starting at the root folder or slash all the way down to the proper location of the file that you're discussing. This is a unique path per every file on the file system and allows you to describe the full-length path that one would start with from the slash directory or root location. Alternatively, relative paths will always reference the location of a file or folder from the current working directory. The concept of the current working directory is where you are currently located on the file system. We'll learn commands that allow us to change the working directory we're currently located in, so that then files will change their relative paths from that location. When we need to describe how to get to a file from the current working directory, we'll use relative paths. An absolute path is oftentimes referred to as a fully qualified name, meaning that you can always start from the slash directory or root location and utilize the absolute path to navigate to the file itself. As you try to traverse the file system all the way down to your location, we'll separate each directory and subdirectory using the /. In this way, if we had a file named messages in the location /var/log, we can see that the location that would denote is written out as /var/log/messages. But please be aware that we start with a slash and then move through the various directories down to the final location of the file name, yielding the absolute path. Let's take a look at this within a terminal. From the terminal, if we wanted to get to the var log messages file, we would utilize a change directory command, or cd. When using the absolute path, we always start from the slash directory. Then we iterate through the subdirectories, var, log. Once we are in our proper directory, we then can hit enter Using the ls command, we can list contents. While many things are here, we can certainly see that our messages file is there. If we wanted to go back to our root directory, we can do so with the cd command and /. If we wanted to see the contents of this file, we could use the command cat, which we learned previously, using its absolute path of var log messages. In this case, our student user doesn't have access to this particular file, but we can tell that the permissions were checked against a proper absolute path. As I mentioned, the current working directory is a concept of your present location within the file system. As you just saw in the previous demonstration, I was able to utilize a command to move around the file system. Relative paths come into play when you consider this fact that you could have changed directories and be located somewhere else throughout the file system. Wherever your current working directory is, your relative path will be changing as you move that working directory. Relative paths will never start with the / or the root directory declaration, as they will always start with a reference from the current working directory. An easy way to tell whether you're looking at an absolute or relative path when someone passes this information to you or you receive it from output is to understand if it begins with a / or not. Absolute paths will always begin with a / and relative paths will not. To see an example of the relative paths, let's go back to our terminal. We know that from our last command, we had a file located at var log messages, and that the cat command would allow us to pass the absolute path there. Using the cd command, I'll navigate into the /var location. Now that we're currently working out of the var location, we can use a print working directory command to see where we're located. Here is where you'll understand a relative path to the file located in its subdirectory and then named messages. We know that the subdirectory in this case is the log subdirectory, and the file we wish to interact with is messages. To perform the same work of the cat command, which we know will give us a permission error, but we'll check for validity of the path, is cat log the subdirectory. Note that we're not starting with a /, but merely declaring the subdirectory in our current working directory, and then the messages file. That's the difference between the two concepts of absolute path and relative path. I was able to just show you the command pwd. As you navigate throughout the file system, the pwd command will print the working directory that you're currently located in. As you navigate around more and more, it'll become important to check this path, especially before executing specifically destructive commands or to help you form the paths to the files you need to interact with. Let's try a few exercises coupling the pwd command, the ls or list command, and the cd command to navigate from directory to directory and change our current working directory. As we looked at the file hierarchy in our previous section, we know that the home directory is created for each user. I have my student user's home directory here. Ask yourself, is this navigation using the cd or change directory command an absolute or relative path? If you said absolute, you're correct. Absolute paths start with the /. If I need to see my current working directory, I can use the print working directory command. If I wish to see the contents of my directory, I can use the ls command. Here you can see the subdirectories, colored blue in my terminal, that are contained within my student's home directory. If I wish to navigate around from this path and needed to go back to the root directory, I could use an absolute path to get there and cd to /. However, other annotations exist for relative pathing. The ...... command says to go up one subdirectory. If I print my working directory after doing so, I see that I've now exited out of the home student directory and am one level of the hierarchy higher in the home directory. If I do so again, I should be in the root working directory. If I now once again go back to the home student directory, I can also string these commands together for relative pathing. If I cd up to the ... that would have been the home directory, I don't have to stop there and could go up twice in the same command. Here, this should take me directly to the root folder. One last shortcut to mention is that a user's home directory has its own unique pathing symbol. If we cd to the tilde key found on the top left of the keyboard, that will always take you to your current user's home directory. If I print my working directory, I see that. And if you remember from earlier in the course, we have the command whoami that will tell you which user you are. If you're ever curious as to which account you're logged in with, especially when switching between several, you can always use the whoami command to tell you your username. From there, you can understand which directory you would expect to land in if you use the cd tilde command. Now that we've found our home directory, this is a great place for us to work with some sample files. Let's try using a new command called touch, which will either create a file if it doesn't exist by the name given, or update the timestamp of access to a file that already does. Let's jump back in our terminal and try this out. Let's touch a sample file. I'll call it sample.txt. If I type the ls command to list out my files, I can see that my new sample.txt command is available. The ls command provides several options. When we use these options, we can get further information about the files we're interacting with. The -l command, for example, gives us a long listing format, or an extensive set of details about the files we're looking at. Let's try ls-l on the current working directory of the home student area we were currently located. Here we can see the type of information given out by the longer listing. Throughout the course, we'll understand what many of these things mean in more detail. Briefly, this will annotate the permissions to our file, permission ownership for the user and group, various details about the timestamp for the file, and then the file name itself. We can see the most recent time that this was accessed. And if we were to touch the same file again, and then do another long listing, we would see that the timestamp has been updated. Additional to the -l option for the ls command are several others. We see the -a, which will list all files, including hidden files, as well as the R option, which says to perform this work recursively. Recursively means that we would see all of the contents from subdirectories as well. Let's try these commands out. If we say ls-al, we now see files that begin with a period or dot. These files are typically hidden. These hidden files are used for various aspects of user customizations throughout the file system and operating system. Just know that while we won't go into the details of the purpose of each of these files, file names that begin with a period or dot are considered hidden files when listing out the contents. When you wish to see these files, you'll need to supply the -a option to the ls command. Clearing our screen, let's try the ls-R command. This recursively lists the contents of all subdirectories. Instead of simply telling us the contents of the directory itself, we can see that should any files exist within any of these subdirectories, we would have listed that out. Let's try the pathing that we learned from the previous section with these new ls commands. If we wanted to do ls on anything other than our current working directory, we can path there with either absolute or relative paths. Let's try /home itself. We can see that we have two users, our demo user and our student users, that each have their own home directories. We could also do this in a similar fashion with the relative pathing. Our current working directory, shown with pwd, is home student. So when we denote .. we're taking just the prior directory. In this case, just the home directory. It would be the same thing as saying ls/home. One other shorthand concept, similar to the ... notation, is the single period. The single dot is the current working directory. Saying ls dot is the same as saying ls. If I needed to move and copy files around, the period notation is a shorthand for saying to do so to your current working directory. It's still permissible to type out the whole path, either absolutely or relatively, for those commands that we'll learn in the future. But knowing these shorthands can save you a lot of keystrokes and time. Adding to your shorthand comments is the idea of the dash. If we cd to the -sign or dash, that will change directories to the last directory we were working in. It seems that our last directory we navigated from was the / directory. If we run the same command again, we should go back to where we were. This is helpful when navigating between two directories to compare or move work around. The dash annotation allows you a shorthand way to refer to the previous directory you were located in. That concludes this section. I'll see you in the next video. Let's have a look at command line file management. When you're ready to create, move, remove, or copy files around the file system, you'll need a series of command line interface commands to do so. We'll take a look at the commands that enable those types of interactions now. Have a look at the diagram that shows some common file management commands. We'll take a look at each of these and give them a practice within our terminal. The first command we'll look at is the makedir, or make directory command. For this command, you'll need to supply the argument of the directory you wish to create. When you're ready to make directories, it's important to make sure you're in the right directory as well as you understand what may be affected. Here, I'll create a working directory I'll call practice. mkdir, or makedir, will create a directory that we specify. In this case, we could take an absolute or relative path. Ask yourself what the absolute and relative paths would be for a locally created working directory called practice. I'll use the relative path and just declare the name to be practice. That will create a directory here named practice. We can see it here. Another way to have created that directory using absolute paths would have required us to iterate through the entire pathing /home/student/practice. While not incorrect, you can see how there's a drastic difference in efficiencies between using the absolute or the relative path in this case. Clearly, the relative path of just stating the word practice was simple. Now that we have a practice directory to work with, we'll look at the other commands so that we can interact within. The cp command, or copy command, allows us to specify a source file and a destination file. As we learned about navigating, I'll cd, or change directory, into the relative path practice location. If I print my working directory, you'll see where I'm located now. We know that we created a sample.txt in a previous demo. What I'll do is I'll use relative pathing to copy that to a new location within our current working directory. I'll use the cp command and relative pathing to the sample.txt file in the subdirectory above. Since I want to locate that in a file here, I can use the dot notation for the current working directory. If I list out the contents, I now see that my current working directory has a copy of that file. This would have been the same as if I would have said /home/student sample.txt and copied it to the absolute path of /home/student, the practice subdirectory we created, and then the same file name. I hope you're starting to realize the difference of value between absolute and relative pathing. Here, relative pathing is more valuable, but that's not always the case. Keep in mind those two concepts as we continue to grow our Linux skills. We may oftentimes want to copy a directory and its contents. When that's our intended result, we'll need the option -r for recursion to the copy command. Let's try that now. We can do cp-r. We know that we have home, student, desktop as a subdirectory, and if we wanted to put that in our practice directory, we could simply use dot, as that's our current working directory. When we now list the results, we see that we have not only the subdirectory, desktop copied in, but all contents within. Unfortunately, the desktop subdirectory didn't contain any contents, but that illustrates that we would have copied the entire directory as well as all of its contents, using the -r option. When we need to move a file to a new file name or rename a file, we can use the mv command. This is useful, like I said, in both renaming as well as relocating a file. We see that we have the desktop subdirectory and the sample.txt, and we're working from the home student practice area. If we wanted to move the sample.txt file to a new name of example.txt, we would use the command move sample.txt, the original file, to what the new name we'd want it to be called. In this case, example.txt. We then list out the contents and see the name has changed. If we needed to remove a file, we'll use the rm command for remove. We'll simply specify the file name we wish to delete with the arguments for rm. Here, let's delete the example.txt file. When we list out the contents, we can see that it's gone. When you need to remove a directory, you'll need to pass a specific flag for -r to remove the contents within. Linux has some safeguards to make sure you don't delete all contents within a directory without realizing they're there, and thus requires you to pass an option flag to do so. Let's do two things. Let's place a file within the directory we saw, and then go through these commands. I'll cd into the desktop directory that we copied over. I'll use the touch command to create a test.txt file. I'll then cd up one directory. That leaves us back in our practice directory, home, student, practice. I'll clear the screen to give us more work. Now we can still see that we have the desktop directory that we copied over. But using the -R for recursion to the ls command, we can also see that it now includes a test.txt file within. To remove the files within the desktop directory, we'll use the rm-r file. To delete the files within the desktop directory, we'll need to use the rm command with the option -r to remove the files within the desktop directory. Now when we say ls, we see that the directory and its contents are now gone. Let's copy it back here so we can learn one more command. Now we have another copy of this. When removing a directory, even if it's empty, the rm command should throw a flag. The rm command by itself without flags will not remove directories. We have another command, rmdir, or remove directory, for this purpose. Listing out the contents, you can see the directory has now been removed. That concludes our section on command line file management. Join me in our next video for a guided exercise on this same subject. Look forward to seeing you there. Welcome to our guided exercise on command line file management. Go ahead and connect to your EC2 instance and let's begin. In our first step, we're asked to make sure that you're in the home directory for your current user by using the cd command. The pwd command should print your working directory and show the home EC2 user directory. The prompt itself will show the tilde as a representation of your home directory. All right, I happen to have already been in my home directory, having just connected, but I'll do a pwd to print my current working directory and show that I am in fact in the home EC2 user. Note that the tilde denotes that this is our current working directory or home directory. In this home directory, we want to create a bunch of files that we'll use throughout the exercise. We'll create 6 files named song and then the numeral 1 through 6, snap, the numeral 1 through 6, and film, the numeral 1 through 6. We're choosing some standard file extensions here of MP3, JPG, and AVI for the corresponding file types. We'll use the touch command to create each of these sets, and you can string all of the file names into a single command. All right, you can see I typed out touch, song 1, 2, 3, 4, 5, and 6, all .mp3s. Let's go ahead and hit enter, and then I'll use an ls command to simply list out those files. They all look correct to me. Just check your spelling so that we can use these files through the remainder of the exercise. I'll now do the same for the remaining snap and film files. A reminder here, now that I've typed out this command, that when I type snap5, my command is simply line wrapping to the next line. I didn't press an enter key or anything of the sort. I've simply hit the width of my terminal at this font size. Double check your work before pressing enter to make sure you typed everything correctly, and then you can go ahead and use an ls command to verify you now have 12 files, all your snap JPEGs and your song MP3s. Last one is the film files. These are .avis. Again, a call out on that line wrap. I didn't press a key there. I'll press enter now that everything looks correct, and I'll do an ls to see all 18 of our files. We have our film 1 through 6, snap 1 through 6, and song 1 through 6. Okay, now we'll proceed into task 2, where we're going to create 3 subdirectories, music, pictures, and videos, in our current working directory, the home directory. So we'll use a makedir or makedir command for this. All right, and then I'll go ahead and do an ls. And they're jumbled in there, but you can see the color-coded directories in blue on my screen, music, pictures, and videos. Task 4 wants us to move the song files into the music folder, the snapshot files into the pictures, and the movie files into the videos. These subdirectories can then be viewed with ls-l in each of them to verify your work. We'll use a single move statement for each of these commands, or the mv command, and then the destination at the very end of that argument. You can see the commands we're going to run here. So let's go ahead and do that. Now, I do recommend that as you type each of these, as I type SO, I can complete that to song. Then I can type the single key for the number I wish, and then the tab key again. It's all about getting faster on the command line. And then all of these files are going in our music folder. I'm using the tab key constantly here to autocomplete the keywords I'm typing. Now that I look, I can see they've all moved. I'm going to continue my work, and then we'll take a look at each of these directories at the end. So I'm going to move all the snap into the pictures folder next. And that goes in pictures. Do an ls here. Okay, all of those are gone. And finally, our film files will go into videos. Here I can just simply type F in order to autocomplete, since there's no other matching terms. SN and SO matched, so when I was typing songs, I needed to be more specific. Once the song files were out of the way, Snap would autocomplete with just an S, and here Film autocompletes with just an F. Then I'll supply the numeral for that particular file, and so it ends up being F tab 6 tab for me. Now I want to put these in the videos folder, and I can just type capital V tab to actually get that shortcut as well. I take an ls of this directory, and then I'll do an ls on each of these in order to see the contents of the file. And it looks like everything's been sorted into its proper subdirectories. Now we want to create 3 additional subdirectories and organize the files into projects. We'll call these Friends, Family, and Work. So here we want to create all of these with a single command. Previously, we ran 3 makedir commands to create the 3 subdirectories, but that's extraneous, and we could have supplied all 3 of those arguments in a single command. Let's try that approach now. Friends, Family, and Work. And then I'll go ahead and press Enter. And if I do an ls, we can see we now have all of our 6 subdirectories. The 3 new ones, Friends, Family, and Work, have been created. Now we want to copy some bits from the music, pictures, and videos subdirectories to Friends and Family. We want to copy anything with the numbers 1 and 2 to Friends, and anything with 3 and 4 to Family. Before each copy, the example also changes directory to the destination directory. This allows us to take advantage of a specific shortcut of location called dot or period, meaning the current working directory. The current working directory corresponds to the output of pwd command, the print working directory. You can either choose to do that and move into each of these directories as the example shows, or use relative pathing in order to explicitly state the path that you wish to move it into instead of CDing. I'll do what the example shows here and actually switch directories and take advantage of the period annotation for the current working directory. So first, I'm going to go into Friends and move all the 1 and 2 files. So I'm going to CD into, let me clear my screen just so we get a little more space here. I'm going to CD into Friends, then I'm going to copy, and I'm going to use some relative notation here. Dot dot means go up a directory, and then if I use my tab completion, I can see what's available to me there. There's some hidden files, which we haven't talked about. They all start with a period and wouldn't typically be displayed, but tab completion shows them. And I want to go into each of the music, pictures, and videos directory. Music, and I want song 1, and I want to put that here. I can up arrow to get to that and just replace the single entry for 2 and do that there. Perfect. Now I want the 1 and 2 of each of the pictures and videos as well. So I'll copy dot dot pictures, and I know that these were called a particular file name Snap, but I could press this tab key to go ahead and get that. And I want Snap 1, press the tab key, and I could put it dot. I'll do that again. Here I'm typing it out, but I am using my tab key. And then for this last one, let's try something a little different. We should be able to do both film 1 and dot dot slash videos film 2 to dot. Nice. When I ls, you can see we had a few ways that we did that, each of them a little more efficient, so that's great. Now that we have corrected our Friends folder, we need to switch over to Family to do the 3 and 4 files. So let's do a quick cd/family. I can show you my current working directory, and I'll clean up the screen just so that we get a little better view of this work. Now for this one, we're asked to do 3 and 4 from each of these folders into this directory. So I'm going to copy 3, and all right, perfect. I can then copy dot dot the pictures, and I want 3 and dot dot 4 to dot. Okay, and lastly, I'll copy videos 3 and dot dot slash capital V tab 4 tab dot. Just wanted to call out what I was pressing, so you see I'm using that tab key a lot. Makes me very efficient. Once I've completed that last one, I've got all of the files, the 6 files we were requested, the 3 and 4 variation of each. Now we want to copy files in music, pictures, and videos containing the numbers 5 and 6 to the work subdirectory. So this should feel familiar. Again, the same work. We just want to do it for 5 and 6 in the work directory. So I'm going to cd to work, show you my current working directory, and let's clean up the screen. Notice that current working directory is also shown here. So if you're ever curious where you are, the directory name is always contained in your prompt. So that's always helpful as you move around a lot here. Now we want to do a very similar thing. Oop, that is definitely not the name of it. Music tab, song 5 tab, dot dot slash, capital M tab, tab 6 tab, dot. All right, and then go ahead and do the same for the others. Great, we can see I have 5 and 6 of all of those files in this. Now we want to clean up and delete some of this work. So let's go ahead and cd up to our home directory as a start, and then clean up and delete some of this work. So let's go ahead and cd up to our home directory as a start, and then we want to attempt to delete both the family and friends directory with a single rmdir command. Okay, we're in our home directory now. We can see as annotated by the tilde, we're asked to use a single rmdir on family and friends to see what occurs. All right, we do get the expected output that this failed to remove the directories because they're not empty. By default, the rmdir command does not remove directories if there's contents within them. This is sort of a safeguard to make sure you don't accidentally delete data, because that's an unrecoverable action in Linux. So now we want to use instead the rm command with the -r flag in order to delete family and friends folders and the files within. So this should work in this case because we're doing a recursive delete of the files and folders. rm-r, family, and friends. Now with tab completion, it automatically tacks on that trailing slash. If you are typing this out, it's the same to have or not have that. I'll go ahead and remove one of them just to show that. I hit enter and I do an ls, and we can see that both of those are gone and all of the contents within went with them. Delete all the files within the subdirectory by cding in, but don't delete the directory itself. Okay, easy enough. cd into work. Again, I'll just wipe my screen and print out my current working directory. We can see that we have all the files, and so I want to do an rm film 5, film 6, snap 5, snap 6, song 5, song 6. Okay, and then we can do an ls, or as it says, an ls-l, which we see has a total of 0 files. Now lastly, we want to go ahead and remove the work directory. We'll use a single rmdir command. Last time that didn't work for us, but it was because the folders contained files. So here we're going to rmdir this directory, and it should go ahead and remove the directory since we moved in and removed the files ourselves. Now, we're currently sitting in that directory, and if we were to try that command without moving out of this directory, without that cd command, we'd likely get an error. Let's try that just to see. If we do this rmdir on work, or I guess in this case it would be dot, let's see what happens. Yeah, you can't remove dot. You're inside the directory. So let's try to be a little more forceful. Let's say home, ec2 user, work. All right, that exists. The path is there. And that works. We can be explicit, but let's go ahead and CD up, do an ls, and it's gone. But did you see that little anomaly that occurred there? I just like to point that out so people are aware that if you do use full path, it can delete the directory you're in, and you're in this sort of limbo state until you CD out of it. All of your files are in fact gone, but you're just still left sitting in there. As the instructions actually said, you should have CD'd out of there most appropriately and then run the rmdir command. I just like to illustrate that little bit of extra knowledge. That concludes this guided exercise, and I look forward to seeing you in our next video. In this section, we'll learn about matching file names using path name expansion. The objective of this section is to make sure that you can more efficiently run the commands we like to use on the command line interactions using the substitution and expansion methods available to you in a bash shell. The bash shell has a number of ways to help make your work more efficient, the first of which is known as pattern matching. We have a number of ways to express globbing or wildcard usage that allows us to express in the bash shell ways to shortcut and identify multiple files with some simple syntax. Have a look at the following table on meta characters and matches. We'll use many of these in the terminal in just a moment, but let's take a quick look at the various ways we have to annotate our interactions on the command line to take advantage of pattern matching. One of the foremost characters we use in pattern matching is an asterisk, otherwise known as a star. When we say star or substitute that with an asterisk, that means that we will replace this particular piece of the pattern with any number of 0 or more matching characters. If you recall from our previous guided exercise, we had a number of files numbered 1 through 6. We could substitute in place of each of those numbers an asterisk character to denote any of those files. We'll see that when we get to the command line with this. A question mark character allows us to replace any single character with a wildcard here that specifies that any character can be used in its place. This does require that a character be in that place, unlike the asterisk above. This must be replaced with any single character. We then get into a number of bracketed annotations, the first of which shows the example of single brackets must start with this character. We can see double bracketed annotations that means some other shorthand keywords. When we say alpha in the double brackets enclosed within colons, we mean that any alphabetic character can be substituted in place there. Lower means that this character must be lowercase. Upper obviously means that it's uppercase. Alnum or alphanumeric means that it can be any alphabetical or numerical digit. PUNCT or punct says that the printable character can be anything that's not a space or an alphanumeric character. Digit comprises the numbers 0 through 9. And lastly, the space keyword says that a single white space character can be used. This means that it could be a tab, a new line character, form feeds, or spaces themselves. Here we can take a look at a few examples in the command line. Let's duplicate this work by jumping back into the terminal. Let's create our working directory. All right, I'm going to make a directory that I'll call glob and CD into the glob directory. I'll clear my screen to begin the work. We can see in the instructions here that they create a number of files: Alpha, Bravo, Charlie, Delta, Echo, Able, Baker, Cast, Dog, and Easy. I'll use a touch command to do the same. Now that I've completed that command, you can see in the listing that I have all of those files. Now that we want to start using some of our pattern matches, let's start with the ls command to list out all the files that begin with A and use the wildcard asterisk to do so. If we say ls a star, we get both files, able and alpha. Now, if I say ls a and I use 3 question marks to denote that 3 characters must be there, this should only match the one that is 4 letters long. And indeed it does. If I were to add an additional question mark, I then get alpha. As you can see, the asterisk allows us to replace any number of characters as a match, whereas the question mark must match a single character in that place. Now let's use a bracketed annotation to do some similar work. We'll look at the A and C words that begin with A or C, meaning that the first character, can be A or C. When we now say asterisk after that, that begin with A or C, and we now say asterisk after that, then it's any number of characters to follow. This gets us all 4 of the words Able, Alpha, Cast, and Charlie. If we were to restrict the number of characters in there using the replacement of asterisk to question marks, we could see something similar as we saw before, which is that we would start with the letters A or C and then followed by 3 individual letters. This only matches Able and Cast. If we just wanted to match on question marks alone, all the 5 character words, we could put 5 question marks and see that we have only the 5 lettered words that show up. Next, we have the concept of tilde expansion. The tilde character matches the current user's home directory. We can also use the tilde command to reference the user that we'd like to interact with. In other words, it doesn't always have to be used for the current user you're logged in as. We can see some example of this below, and we'll jump into our terminal to replicate this demonstration. We can see our current working directory is the home student glob directory we were just in. If we ls tilde, that references home student, and we can see the contents of the home student. If we ls tilde student, we can see the exact same by specifying the username. Since we are the student user, this information matches, but we can use tilde to replace with other usernames. In this case, the root user is not a user we have access to their files, and therefore cannot see the listing. We also have a demo user that we don't have access to as well. Moving from the table we saw above into brace expansion, braces allow us a way to clearly delineate out some other ways for pattern matching that can make our commands more simplified or explicit for matching purposes. The braces themselves will contain a comma-separated list of strings or a sequence expression. This allows for some more explicit matching scenarios or expansions depending on our usage. Let's take a look at a few examples as we jump back into the terminal. We remember creating a number of files that all had the same file structure essentially, like snap1, snap2, snap3.jpg. We can use our braces to go ahead and create files in a more elegant fashion using the brace annotation. If we wanted to touch a file that was called snap and we needed snap 1 through 6, we have a way to use braces, 2 braces, and then the extension.jpg. Now all of them will take this form snap, some other character.jpg. And what we want them to have within is the numbers 1. And then if we wanted to, we could iterate this all the way up however high we'd like to go. Here, we can see an example in the notes of iterating all the way up to numbers 1 through 3. In this case, they're using the echo command. I'll continue to do this work using the touch command. Let's do file 1 through 3 of snap.jpg using the touch command. When I then type ls, we can see that snap 1, 2, and 3 was also created. Creating files in this fashion allows us to easily create files of a like name structure with simple annotations in the braced syntax. We can do more explicit things by combining some braced syntax expansions. If we touch file, and let's say each one needs to have a letter and then a number, and we want to create all combinations of 1 and 2 for the number and A and B for the letter. We'll do the first set of braces with 1 through 2. I'm going ahead and writing it out as if this could be a very large range, but with numbers 1 and 2, you have just the 2 entries themselves and could have just listed them explicitly. Then we'll do A through B and give it the extension we'd like to add to that file. When we look and see what was created, you can see that we have file 1A, file 1B, file 2A, and file 2B.txt that got created. Lastly, we can embed one set of braces within another. This allows us to have differing sets of files created depending on our needs. Let's say file A has a version 1 and 2. Let me do something different than files so that we get different files output. File, let's still say A, but let's say A has a 1 and a 2, whereas B and C can just be comma separated values. Let's just call this .out to get a different file extension. We then take a look and we get test A1.out, test2 A2.out, but then test B and test C do not have the 1 and 2 versions. In this way, you can craft together all the various brace syntaxes you need for these expansions. A practical use as called out within the instruction set here for brace expansion is to quickly create a number of files or directories for your work. You can see an example of the make directory command here, creating a RHEL 6, RHEL 7, and RHEL 8 directory. While this is a real-world use case, you can see that it's not limited to just the make directory command and can be used for copy, move, touch, echo, make directory, or even remove commands. Brace expansion is valuable all throughout the Bash terminal. Variable expansion is a next concept that can be very powerful within the command line. It's not an uncommon task to need to store some value within a variable and then recall that information whenever you execute commands or are doing configuration work throughout the system. We can see the example shown here of how to set a simple variable name and its value. Note that we're not using any spaces between the variable name, the equal sign, and the value we wish to store in the variable. Let's create a simple variable now, and then use the information shown in the second box to recall that variable. We'll use the echo command to recall the value of a variable. When we recall the variable by name, we use the $sign to denote that it is a variable. The echo command will then interpolate the variable name into its value. Let's create a variable named test_var and set it equal to the test info value. Now that variable's set, we can use the echo command to echo out our test_var and see that its value is test info. This is the basics of variable creation and then substitution that you can use throughout all of your work as you grow as a system administrator. In case you're stringing together really long commands, you can also take advantage of the brace syntax to enclose your variables and ensure that they don't interact with other output. With a simple writing out of a variable as we just did, that's not necessary, but as you string together more elaborate bash command strings, this may become a more prudent approach. I'll show you simply here that we can do the same thing with the variable we just created. Using the other syntax would still include the $sign and then open up and close a set of braces that include our variable name. We do see that the same value is returned for the variable test_var, or namely, the output test info. It's super powerful to be able to input the output of a command into sentences or structures. You can continually do this as you write your first programs later on in your system administrator exploration or even further in the course. But the output of a command such as date can be interpreted in real time when we execute the commands. Let's take a look at some of that on the command line. We'll use the echo command so that we'll be able to interpret the date here. We can then say today is, and then now we want to actually have the system input the date itself. Here, you can see an example of that we can use within our terminal. This is using the date command to input the date on the command line, as well as some additional formatting options to that command so that we output exactly the aspect of the date output we wish to display. I'll start by just echoing the date, and we'll work from there. Here we'll use a $, open a parentheses, say date, and close the parentheses. Today is, and we get the entire output of the date command. By running the command by itself, you can verify that's the case. As we see in this example, however, it may only be useful to have a single field. In this case, the field that shows the name of the day. If we wanted to do that, we can use our up arrow and go back and continue to add the additional options, namely the plus, parentheses sign, and then the capital letter A. So we'll say plus, the parentheses sign, and the capital letter A. Today is Thursday. Indeed it is. Now please be aware, if you're doing this work on a different day in your environment, then certainly you would get different output. And if you're seeing the wrong output for your actual day, then consider that the date and time may not be set correctly on your individual machine. You can verify the correct output by always reviewing the proper output of the date command itself. We can see an additional example of using this type of work included in the instructions here. Here they're using a much more elaborate version of the same type of approach. In this case, using the minutes value extracted out of the same date output, as well as the time in an hour format. I think something that's important to realize here is that in previous versions of this approach, a command substitution used the backtick character. This character is found on the same key as tilde in the top left of your QWERTY keyboard. If you see other people doing this type of approach or see it in use in scripts or tooling that you encounter, know that that's just a previous way of doing the same type of substitution. While modern RHEL implementations take advantage of the annotation we showed here, it's still okay to use that. However, you may encounter that, and I did want to call out what it looks like and what it does, that it is something similar to what we're using in this more modern environment. Now, occasionally you're using work of this nature, but you actually need to output something with the meta characters themselves. We have a method for protecting arguments from expansion. We'll use the / character when we need to tell the terminal to not actually interpolate the variable, say $home, into its stored value, but instead actually print the literal string $home. Let's show an example of that. If we want to type a sentence that says something like, "You are $home," we can do that, and it will tell us you are in the interpolated variable output for /home/student that is stored in the variable $home. But sometimes we may just want to literally print the phrase $home, at which point we would need to tell the terminal you are, and now use the / to tell it we don't want it to substitute $home to its value. Now we'll get the output of $home literally printed. This is also known as escaping the meta character, or in other words, just telling the command line interface to not perform the expansions we're used to seeing when we use these special meta characters. Additional ways to protect longer character strings are the usage of single or double quotes to enclose the arguments. We can see that called out here. Additionally, an example of using double quotes is shown here, allowing it to print out the specifically iterated values between those double quotes, as opposed to considering that an asterisk or these $braced annotations could be interpolated to variable substitutions or wildcard expansions if left unattended to. That concludes our section on command line expansions. I look forward to seeing you in the next video. Welcome to our first lab in the course. This lab is on managing files with shell expansion. All right, we're asked to create the files in the first step, so I'll go ahead and do that now with braced annotation here. So we're going to touch TV _ season, and we have 2 seasons, so it's 1.2, and then episode, and we have 1 through 6 of those, and they're .oggs, I believe. So there we go. We can go ahead and hit enter and do an ls on that, and we can see exactly what we expected. Season 1, episodes 1 through 6. Season 2, episodes 1 through 6. Perfect. We were specifically asked to only list the TV files. Since I have some subdirectories, let me go ahead and do that wildcard listing. Now we want to create our mystery chapter files 1 through 8. No problem. Very similar skills, so we'll touch mystery chapter, and we have 1.8, and these are .odfs. Okay, and then we want it to lsmys wildcard. Oh, got to hit the right key there. And we do see our 8 files. All right, task 3, we want to make the directory in the video subdirectory season 1 and 2. So I'll use the -p flag here, even though my videos subdirectory exists. For those of you who may not have had that in place, this came from previous guided exercises. So I just want to show what would be most correct given if that wasn't there already. All right, so I'll type make dir -p to create all of the parent and subdirectories. And then that's going to be in the videos. And I have season, and then I have 1.2 subdirectories. And I can see that I have those. Now pay no attention to those existing files. Those existed from a previous exercise. All right, now we're asked to move all the season 1 files into the season 1 subdirectory, season 2 files into the season 2 subdirectory using a wildcard. So still located in my home directory, I'm going to move all of the season. Let's take a look at our files. I'm going to move all of the TV season 1 star to videos season 1. And I can just do a real simple up arrow, delete and replace the 1s to 2s to get the same. If I do an ls, Those are all gone. And if I do an ls dash lr on videos, I should see that I do have both season 1 and season 2. And then if I do, let me clean this up, ls on videos season star, I can get the contents of each. Looks good. Now, whereas to make us a nested set of subdirectories, so here it will require the -p flag no matter. So I'll definitely need to use it here. So I'm going to make directory -p. This goes in my documents folder. Documents, my under bestseller, and then chapters. Right? Yeah. So then we can do ls-r documents, and we see that it has the my bestseller directory with the chapters directory beneath that, with no contents in the chapters directory. Let's clear our screen. Challenge to do so in a single command. We create the 3 subdirectories: editor, changes, and vacation. So let's do that now. Make dir. It was documents and then bestseller. Then we have 3 arguments that we're going to create: editor, changes, vacation. Editor, changes, vacation. Then we'll do an ls-R documents once again. And we can see that we have those 3 subdirectories. None of them have any files in them. Now we want to change to the chapters subdirectory. We need to be sure to do so in a single command. From here on out, those single commands will be necessary, since some tasks require us to use a shortcut that only works if you've input the correct commands. We're going into chapters. Okay. Now we're asked to move the mystery chapter files into the current location using the dot shortcut. Well, not specifically using the dot shortcut, but I certainly will. We're asked what is the simplest syntax, and I believe in this case it's taking advantage of both the tilde and the dot annotation. The wildcard as well is certainly helpful here. So we'll move tilde, my tab completion star, right? And then we're going to put those here. Dot is a really easy way to remember that, is dot is here. So whatever your current working directory is, the period represents that location. So if I do that and then I do an ls, I see my 8 chapter files. Now we're asked to move chapter 1 and 2 into the editor subdirectory, a tier up from where we're currently located. So let's do that. Move mystery chapter. We know we want 1.2, and that's a .odf. We want to put that over to the editor. Okay, now we can ls./editor and see those files. We want to move chapter 7 and 8 to vacation and verify that that landed. Okay, easy enough. Now I use ... for my notation in the braces. 1.2, you can see. Here, I'll use a comma. Okay, and then we'll ls ... vacation. Now just to go ahead and call out what was different there. 1.2 is all the numbers between 1 and 2, the range. So that makes a lot of sense if there's 10 numbers. If we do 1.8, okay, for example, that's 1, 2, 3, 4, 5, 6, 7, 8. It was perfectly fine to do a range from 1 to 2, but it did add an extra character we didn't have to type in the name of 2 periods instead of 1 comma. When it was 7 and 8, we're listing individual elements. Here, the range from 7 to 8 certainly works because there's no numbers between 7 and 8. However, listing the individual elements of 7 and 8 separated by a comma may be more useful. If we said move the odd numbers, you couldn't use a range there. You'd need to use specific elements, right? So 1, 3, 5, for example, would be a really good implementation of using the comma to list individual specified elements versus a range from A to B. Okay, we moved those. We verified those. We're on task number 10. We want to CD. I think this is where the CDing may begin to get quite finicky, so paying close attention to that. I remember that in our instructions when we reviewed them. So we want to CD to video season 2. Okay, all in a single command. That's easy enough. CD videos season 2. I can go ahead and print my current working directory to verify that. We want to copy everything with episode1.ogg to vacation. All right, easy enough. So that's a copy command. We're copying, not moving this time, and it's episode 1 to vacation. So we CP. They show using a star. I used a tab. Tab for me completed that whole thing. It certainly makes sense to use a star. It expands to the same thing. Just show you a different alternative there. Now we're asked to put it in the home directory, documents, my bestseller, vacation. So let's go ahead and type that out. All right, and then let's just do a quick ls on documents, my bestseller. Great, we have that episode listed there. Here's where, with a single cd command, we want to go back to the vacation directory. So let's do that first. I'll show you my current directory, and if I cd, the shortcut we were looking for was dash. I'm now back in, oh, I see what I missed. I need to cd back to here. All right, then I'm going to cd to / documents, my bestseller, vacation, right? ls. I had done an ls without cding there. So between my bestseller and vacation, return to vacation using the cd shortcut again. And I have. So now you can see cd, there's my season 2, cd, there's my vacation, right? Okay. Really helpful to take advantage of that dash or minus sign annotation for your last working directory. Okay, now I want to cd up a directory. Let's just do that first. Should be in my bestseller, and I am. We want to copy chapters 5 and 6 to the changes. All right, so let's CP. All right, we'll cd chapters, and we wanted chapter 5 and 6. I'll use brackets here and individually list the elements. And those are I believe, ODFs. Yes, they are. And I want to put that in, typo, in the changes directory. So let's ls changes, and we see that we have those there. Now we do still have them in the chapters as well. That was a copy, not a move. So be advised, these instructions are very explicit when you're supposed to copy and move. Now we have the last little transformation bits we want to do here before we start making our way out of the exercise and cleaning up some of our work. So we want to cd in there. And now we're going to do some additional files that include these date stamps in the file name. So we're going to copy chapter 5 to one that includes the chapter 5 with a little date insert. We'll do that 2 different ways. So let's go ahead and do that now. Now I go ahead and use some tab complete to do that before I then come back, and I'm going to put in our expressions. $, open some parentheses, and then inside date plus %F. So here it's an underscore $, open close some parentheses, the date command, and then I want a plus %F. Okay, when I do an ls, I get that expansion there. And for the other one, I just need to come hit the up arrow, replace F with S, and I'll get that other file name there. Perfect. Okay, now delete the changes directory in the following way. First, delete all the files. Let's do an RM mystery. Mine says RM mystery. The tab completes it all the way out. But just to be cool, I'll clean that up and do RM mystery star. We're all done. Then we want to cd up a directory, remove changes. Oh, but that's a directory, so that doesn't work. So now we want to use the remove directory command for changes. And we can see the changes directory is now gone. All right, we've gone on vacation and enjoyed those files and such. But when it's over, we need to just get rid of that vacation directory. So we'll delete it using an rm command with a recursive option, or the -r flag. So let's see, we're still here, pwd. If I do an ls, I see my vacation. And I can do an rm-r v and then hit my tab key, and it auto-completes out vacation. Do an ls, and I see that it's no longer there. That concludes this lab, and I look forward to seeing you in our next